So we discussed last time how a factorial worked. Remember, a factorial counts the number of ways that we can arrange a certain number of objects. So if we had 7 factorial, that would be 7 times 6, times 5, times 4, times 3, times 2, times 1. You would just multiply it through. Now, whatever that comes out to, it looks like that would come out to 5,040. Your calculators should come equipped with this factorial operator, the exclamation mark here. And that's going to tell us what to do here. So the exclamation mark is very specific in mathematics. We argued 0 factorial is equal to 1 for certain reasons. So yeah, in your calculator, whether you have the TI-83, 84 graphing calculator, or if you have the standard scientific calculator, you should be able to find videos on how to compute these things, factorials, permutations, and combinations in the Canvas modules for Chapter 5. So check that out. If you have a different kind of calculator, just do a quick YouTubing, do a quick search online for your type of calculator and how to do factorials, combinations, permutations. So now, whenever we are wanting to order a large group of objects and just take a subgroup of a certain size from that. So for instance, a Little League baseball team has 13 players. The coach has to choose a batting order for 9 of the players. So basically, 13 kids are playing some Little League baseball, but only 9 of them are going to end up batting in the game. The other 4 are going to get benched. How many ways could the coach do this? How many ways not only can the coach pick 9 out of the 13 players that the coach has available, but also reorder the 9 different players themselves, because there's a lot of different ways you can take 9 people and put them in a batting order. So the first choice that the coach has, well, for the very first position in the batting order, the coach has 13 players available to make that. For the next position in the batting order, the coach has already picked 1 out of the 13 players, so the coach has 12 left for the second position. And then you can reason the coach has 11 left for the third position, 10 for the fourth, and so on. And so for whatever that equals, you can, do it in your calculator. It looks like we were starting to compute 13 factorial, but since there were 4 that were left on the bench, we divide off 4 factorial from it, which is exactly what we did. We divided off 4 times 3 times 2 times 1 out of it. And so this is not a coincidence. This is actually an important computation. But basically, the coach did 2 things here. First, we counted the number of ways of selecting 9 of the 13 potential batters. But the coach also did this, counted the number of different orderings / arrangements of those 9 players picked. In general, we're going to see that that is exactly what a permutation does. That is exactly what a permutation does. So let's scroll down here. you have a permutation of n objects taken r at a time. NPR is what we usually call it. NPR. So in our example, we had 13 batters, potential batters, P9. 13 P9. Thirteen batters taken, 9 at a time. And so I'm going to get out my calculator here and work it with you. And we're going to see that that's going to be a pretty large, excuse me, that's going to be a pretty large number. And it almost doesn't even make sense, but it actually makes perfect sense when you think about it. $259,459,200 different ways. That's wild. You just have 13 little league kids who want to play baseball. There are over 259 million different ways that you could pick 9 of those kids to be in the lineup, and also rearrange all of the kids you do pick. So a pretty interesting idea, the permutation. We can work a couple of kind of word problems here to really drive the point home. A comedy club has amateur night. 6 people volunteer to tell a joke. Anne, Bill, Carl, Dan, Emma, and Fred. And what convenient lettering here, because it's A, B, C, D, E, F. Once they tell their joke, they are done. How many ways can they tell the jokes without retelling any of the jokes twice? So basically, how many different ways can we permute the 6 people here? How many ways can we take 6 people and then choose all 6 of them and then rearrange those 6 people? So you could just automatically jump the gun and say that's 6 factorial. You could also say that's 6 permute 6. 6p6. It's the same thing. And that's going to turn out to be 720. 720. Twenty equally qualified friends are going into business together. They need to pick a CEO, operating manager, and a treasurer. How many ways can they pick these? So we need to figure out from a pool of 20 objects, how many different ways can we choose 3 of those objects? And then once we've chosen 3 of those 3 objects that we need, does the order matter? In other words, once we've picked the 3 objects from the pool of 20, does the number of orderings of the 3 objects matter? And one of the nice phrases you'll see is, does order matter in this situation? If order does matter, we need to do a permutation. If order does not matter, we need to do something called a combination that we're about to just start here in a second, start learning about. Well, let's think about it. Once you've chosen the three people, then you've got to put them into a group consisting of CEO, operating manager, and treasurer. CEO, operating manager, treasurer. Once you've picked your three people out of 20, let's say you got, use a different color, Bill. Let's say you've got Ginny. And let's say you've got Ron as the three people who were picked from the 20. Well, this once you pick those three, you could put them in this order. Bill's the CEO, Ginny is the operating manager, and Ron is the treasurer. But there's actually a bunch of different ways you could reorder those six people to fill, or excuse me, those three people to fill those roles. And so actually the order of the group does matter even once you've picked the 20 out of the three. So a very much yes, order matters because you have three named positions that you're trying to fill. It's the same as if you were running a race that we're going to do here in this next one. Not only do you need to pick your top three finishers, but the order in which they finish does matter. So we use a permutation. And so there's a couple ways we can see this one. You could say, well, let's think. From the group of 20, there's 20 people we can pick into the first slot, times 19 we could pick into the second slot, times 18 we could pick into the third slot. Multiply them all together. Or you can say that that's just a permutation, 20 objects taken 3 at a time. And so we can whip out our handy dandy calculator, and you're going to get 6,840. So 6,840 ways to pick three people from a pool of 20 and rearrange those three people. And so we're done. Finally, on this last one, suppose 40 cars start at the Indianapolis 500. How many ways can the top three cars finish the race? Well, here order matters. Once we pick 3 out of the 40 cars to be the top 3 finishers, the order in which those 3 cars finish absolutely is important because that determines first place, second place, third place. And obviously, first place is better than second place because if you're in first place, that means you're the winner. And when you're the winner, a lot of magical things happen. When you're the winner, you get to do whatever you want. All right, that's what it means to be the winner. To quote a little, if you've ever seen Talladega Nights, The Ballad of Ricky Bobby, which is a satire, a little bit of a fun satire with Will Ferrell. It's hilarious. It's a great movie. It's about a NASCAR driver. And, you know, he learns some life lessons and whatever. But anyways, so this is clearly just a permutation of 40 objects taken 3 at a time. And it's a permutation because the order of those 3 objects matters. And so let me bust out the calculator. That's going to be 59,280 different ways that the Indianapolis 500 could have its top 3 finishers, which is pretty wild if you think about it. There's 59,280 different, basically, finishes of the race if you only care about the top 3 people. So that's pretty interesting. Now, realistically, you have your super talented people, and so we haven't brought probability into this yet. All we've done is counted the number of ways it could finish in theory. But in reality, you're going to have, I don't know any Indianapolis 500 drivers. I know a couple of NASCAR drivers. So, you're going to have your Dale Earnhardt Jr.'s near the top, and your Jeff Gordon's. When I was a little younger, Jeff Gordon was like the hero of everybody in Texas. I think he was from Texas, or maybe not. If you know NASCAR and I don't, and I'm saying wrong things, I apologize. But for some reason, Jeff Gordon was really big in Texas. Very popular driver. So yeah, you're only a certain group of drivers are gonna be likely to finish near the top, but every once in a while, surprises happen. So that's a permutation. How many ways can you rearrange the letters in the word combine? Well, there's 1, 2, 3, 4, 5, 6, 7 different ways. So that would just be 7 factorial, which is the same actually as 7p7. Take 7 objects and permute all 7 of them. It's the same thing. And that would be the 5040. How many arrangements can be made using just 4 of the letters in combine? So you take any 4 letters in the word, and then you rearrange those 4 letters. Why would you want to do that? I don't know. Maybe you're bored on a rainy day and you're interested in running a neato little experiment. Have at it, I say. I think that's fun. That would be 7p4. Here we go. 7p4. And with a little bit of fun here, you get 840. Do some calculations. So that was a permutation. But now we need to talk about a combination. A combination does a lot of the same things that a permutation does, except the major difference is once you pick the smaller group from the larger group, you don't care about the order of the larger group. You don't care about the order of the larger group or the smaller group. It just doesn't matter. So earlier when you were picking, you had a pool of 20 employees and you wanted to see how many different ways you could pick a CEO, operating manager, and a treasurer. Once we picked the 3 out of the 20, then we had to reorder them. But in general, if you just wanted to say, okay, let's say this company with 20 employees wanted to know all the ways it could pick a committee, a special committee to go investigate something. And then you'd pick 3 people, but they were all just individual committee members and there were no title differences between those 3 people. Then you're talking about a combination, because the order of the smaller group of 3 here does not matter in the case of a combination. And so that's really going to be the key difference here. Is a combination, the order doesn't matter. We're going to use, instead of using P, we're just going to use C. So for instance, you could do 20 C, I don't know, 5, or we'll use 3. This means from a pool of 20 objects, how many ways can you select 3 of the objects And once you select the three, you don't care about the number of ways they can be arranged. You're just saying, okay, from a pool of 20, pick three. And once you've picked the three, that's it. They're here in this group and they're all the same element. They all have equal rank inside the group, if you will. And so that's going to happen. You're going to see that a lot. So the combination is perhaps a little bit more commonplace. Imagine if you're a teacher and you have 26 students in your class and you wanted to know all the different partnerships you could make because you wanted to make groups of 2 for a project. You would just say from 26, you would do a combination 26C2 there, because once you've got people in a partnership, you don't care about flip-flopping them or who comes first in the partnership. That doesn't matter. They're just partners. They're just a group of 2 working on this project together. So it just isn't. It's all about what you're trying to do. What are you trying to achieve? What is your goal in a particular situation? We're going to look at the formula for a combination here in just a moment. We're going to see how it works. It looks similar to a permutation, but there's going to be one little extra bit thrown into it. So let's look at a fun one. Let's look at a rock and roll example. Okay, I didn't mean to do that, but boom, I just underlined all that in green. So the USA Today, USA Today, friends, was something called a magazine. A magazine. Now, I know magazines have been extinct for many thousands of years, but a magazine was a printed publication. That means it was not necessarily on your phone that you would access. And no, you guys know what a magazine is, so I'll stop making this joke. It's kind of corny. It's kind of, if you know, like boomer humor, where they talk about like the kids are at the beach and then they make with the sand at the beach, they make a tablet out of the sand, and then they put what they want to watch on the tablet. And the boomer comes up and says, "Really, kids, you always got to be on your tablets and your iPhone." That's boomer humor for you. If you like that, that's fun. Another popular boomer humor joke, and this was from like the year 2000. I remember this. It was like a comic strip, and it was really poorly drawn, and not a lot of effort was put into it. And it's like a father is asking his son to like come downstairs and talk about something, and the son's like, "Dad, I'll just email you," or something. I don't know. This is corny. So anyways, back to it. So USA Today talked about 6 movie/rock stars that achieved cult status after death. Just kind of weird because, well, there's a cult of personality about these 6 people. And that's actually pretty darn true. These are some pretty big names. Marilyn Monroe is a huge name. James Dean was a very famous movie star. He made only 3 movies in the 1950s where he was a lead actor. But all 3 of them were pretty big hits and pretty memorable. Rebel Without a Cause is a classic. And then he unfortunately passed away while young. Then you got some rock stars. You got Janis Joplin, Jimi Hendrix, of course, Jim Morrison, and Kurt Cobain of Nirvana. So some really big, heavy-hitting names. Now let's say you want to make a documentary about 2 of these stars. Well, what you need to do is you need to pick 2 out of the 6 to make your documentary about. And you don't care, once you've picked the 2, it doesn't matter which order you do them in. You're not going to say, okay, I need to figure out the number of ways I could have my documentary, and then I'll do Kurt Cobain first, then I'll do Janis Joplin in the documentary. That doesn't matter to you. You just have these 2 people. Maybe in your documentary, you're going to compare and contrast their lives and find some similarities that people didn't know about them. So that might be interesting. I would bet that a Jim Morrison, Kurt Cobain documentary would be really cool, It'd be especially cool because they are part of a very infamous group of famous musicians, and in some of them were movie stars who died at exactly age 27. And there's actually a lot of people in that list, and it's a really interesting list. So Kurt Cobain and Jim Morrison um, were two of those people. But anyways, this is just a simple combination. It's going to be 6 combination 2. And we haven't put the calculation on here, but your calculator can handle that thing. In fact, if you've figured out where the permutation is on your calculator, then you've actually also figured out where the combination is, because in almost every calculator, they're going to be right next to each other because they're just such similarly linked ideas. So we need a combination of 6 objects taken 2 at a time. And so that one's going to end up being 15, but we'll look at the computation for that in a moment. So a combination just says, hey, how many ways can I pick a smaller group from the larger group, and then just not worry about the order in which that smaller group appears. It doesn't matter. So the combination, we would say NCR as opposed to NPR in that particular case. And we would do n factorial. Then on bottom, we would do n minus r factorial, just like we did with the permutation. But there's a little bit of extra cheddar here on bottom. We also divide out by r factorial, if you will. And so that makes for some interesting implications from that. Of course, if you can find it in your calculator, the NCR tool, usually what you'll do is, so let's say we wanted to find 7C3, you would put 7 in your calculator first. You'd drop a 7 in there on a blank, fresh line, and then you'd go find the NCR tool, bring it up, bring it next to the 7, and then do 3. So you might see it like this on your calculator. You might see, you put the 7 in first, then you go find the NCR operator, bring it up, and then hit 3, and then hit enter. That might just be what you do. And so let me bring up my little permutation or combination calculator that I have. I have some deep magic. And so 7C3 is 35. That's going to be equal to 35. And again, you can memorize this formula up here and use it. Just do the formula and use factorials. But it's so much better if you just go quickly figure out where the NCR and NPR and factorial tools are in your calculator. They're usually all in the same place or very close to each other. That's usually how it works. Some of your calculator will just straight up have an NCR and NPR button. You just might have to hit the second button to bring it up. So there's some kind of interesting implications from combinations we got to really look at. So earlier we did that problem when we were talking about permutations, where we had 20 people going into business together, and we wanted to know all the ways we could pick a group of 3 of them to be CEO, operating manager, and the treasurer. Here, once we pick the 3 people, they're all just going to be, we're just going to give them all the flat name of boss. Hey, you're the boss. And it's not necessarily going to be Tony Danza who's the boss. It could be any number of people. And so here we need the number of ways we can pick a group of 3 from a larger pool of 20 objects. And I'm just calling them objects. No, I don't think human beings are objects. but technically they are objects just in the very broad sense of the term object, which is kind of just another word for thing. They're just things. But that doesn't, that has no bearing on my actual feeling about humanity and their feelings about things. That's not true at all. I don't think they're objects. It's just a convenient term to generalize it. So we want to know the number of ways to pick a group of 3 from a larger pool of 20 objects. Here, though, the order of the 3 objects, once we've picked them, is or does not matter. Once we've picked the 3, they're all just bosses. We don't need to rearrange them into the roles of CEO, operating manager, and treasurer. So this is just 20 C3PO. I wish it was C3PO because I love the Star Wars movies. And if you've been in my class, you know how much I love Star Wars. Why do I love Star Wars? Because it's amazing. Do I love the new Star Wars movies with Kylo Ren and stuff and Rey? No. Do I think those characters suck? Actually, I don't. I kind of like Kylo Ren. I think Rey is a perfectly charming character to watch on screen. I just think the stories suck. They're really, really awful. Whoever made the new Star Wars movies, and I know who made them, and I will not utter his evil name because I don't want to give everybody a chill, whoever made the current modern 3 Star Wars movies ought to be ashamed. And I say that, and they're laughing all the way to the bank and buying, 300 new mansions a day because of that Star Wars money, but whatever. Anywho, that was just to buy time, that little rant. There's 1,140 different groups of 3 we can make from a larger pool of 20. And then once you have the group of 3, you don't care about rearranging them. The number earlier was much larger than that. It was, over 6,000 because we cared about the ways we could arrange the 3 people. But here we don't. This one's super interesting down here. In poker, remember we've looked at decks of cards before, which is technically a standard 52 card deck, is actually called a French deck. It's called French deck. In poker, if you're playing certain standard games of poker, 5-card draw, 5-card stud, which is kind of old school. Now everyone plays Texas Hold'em. Not everyone, but most people, most of the time when you see World Series of Poker and stuff, they play Texas Hold'em. So first of all, it's great to see the state of Texas being represented in a manner like that, and I really like that. But I don't know why Hold'em is so popular today. But imagine kind of older school poker. You're just given 5 cards to make a hand, and you got to do what's best with them. What are the different number of hands you can make? So let's think about it. How many different hands can you make in poker, basically? How many different 5-card hands can you make? In other words, how many different groups of size 5 can you form from a larger pool of 52 objects? And in poker, it does not matter what order you get your hand drawn to you, because whatever your hand is, you're going to look at it and decide what you have. It doesn't matter if you got the King of Hearts first or as your 3rd card or your 4th card or your 5th card. Who cares? You're going to just arrange them in the way you want in your hand, no matter what order they're given to you. So here, order does not matter. You don't care which way you get the 5 cards drawn to you, dealt to you. Who cares? So this is just going to be a combination. This is going to be 52 C5. This is a very famous computation in mathematics, and it's going to be a massive number. It's going to be hilariously large. It's going to be this number. Let me just copy it over here. $2,598,960. Wowzers. Yowza. That's a lot. That's huge. There are almost 2.6 million different hands you could get in a single game of poker. What we're going to do here in just a second is we're going to calculate probabilities based on combinations, permutations, and we're going to see that, oh, well, if I wanted to know the probability of getting a royal flush, well, there's only 4 royal flush hands possible in poker out of 2,598,960. So we're going to do 4 divided by 2,598,960. And we're going to see that the probability of getting a royal flush is tiny. It's the rarest hand, and thus it's the most valuable hand in poker. It will beat any other hand except another royal flush, which you're not likely to get 2 royal flushes in the same play of poker, in the same round of poker. So really the heart of the matter is not only a song by Don Henley, the former Eagle, the heart of the matter is also, can you decide when should you use a permutation and when should you use a combination? So it's just situation by situation. 6 students are running for student government president, vice president, and treasurer. The student with the most votes is president, second highest votes, vice president, third highest votes is treasurer. But we're not going to worry about that so much. We're just going to say the number of ways that the election can turn out. Here we want the number of groups of size 3 from a larger pool of 6 objects. That's what we want at the end of the day in brass tacks. The order of the group of 3 does matter. The order matters here because they are 3 unique named positions. There's the president, vice president, and treasurer, which are 3 different things. They're not all equal in rank, if you will. So that's actually going to be a permutation. You're going to just permute. You're going to take 6 objects, permute 3 of them. Let me do that math real quick. That's going to be 120. So there's 120 different ways the election can turn out. Well, it's just kind of interesting. So out of only 6 people, you can count up 120 different things from that 6. That's kind of interesting. The numbers get really big really quickly. Let's look at this next one. 6 people are on the board of supervisors for your neighborhood park. A 3-person committee is needed to study the possibility of expanding the park. How many committees could be formed? Here, it's a combination. Here, we want the number of ways we can pick a group of 3 from a larger pool of 6 objects. The order doesn't matter because they are all just committee members. Once we choose them to be on the group of 3, you're a committee member, you're a committee member, you're a committee member. There's no different ranked positions, if you will. So this is going to be a combination, just 6C3, which is going to be 20. So actually, there's almost always for the same N and the same R, there's almost always going to be way less combinations possible than permutations, which makes sense because a combination doesn't also count the rearrangements of the smaller group. The permutation does. So the permutation is naturally going to carry with it more. It's going to carry more with it. Baskin-Robbins offers 31 different flavors of ice cream. One of its items is a bowl consisting of, let's not say 3 scoops. Let's just spice it up to make it a little bit interesting. Let's say you're going to get not 3 scoops, but folks, this is America. And in America, you have something called freedom of choice. And if you want to get 5 scoops of ice cream in a single sitting, well, I don't suggest that just from a health perspective. But you know what? Let's say you just got a new job. Or let's say you just got some really awesome news You found a new place and you want to go celebrate. You got a promotion, you're graduating college, you got an A in your statistics class, you're happy. You know what? I'm just going to say it. Go out there and have a little celebration. I think it's important to mark certain occasions, celebrate them, and have a little bit of fun. So we're going to have 5 scoops of ice cream, all right? And I'm proud to say that I would naturally want to engage in that. Um, how many different bowls can you make if you have 31 flavors to choose from and you're going to get 5 scoops of ice cream and each of them is going to be a different flavor? You're not going to get 2 scoops of strawberry and then another scoop of chocolate or something. You're going to get 5 different flavors because, again, this is America. This is a combination. This is a combination. All we care about is the number of groups of 5 we can make from a pool of 31 objects. Once we have the 5 in our group, we don't care how they are ordered. Let me just not spell today. We don't care about how they're ordered. You got 5 scoops in your bowl. Who cares what the leftmost scoop is? And then the next, who cares? You're going to eat it all. So this is a combination. This would be 31 C5. And we're going to find that number to be very large. Let me calculate it real quick using my magics. It's going to be huge, over almost 170,000 possible ways. 169,911 different ways. So you just kind of have to know when to use a combination, when to use a permutation. There's also another important thing. You might need to mix combination with fundamental counting principle. Remember, we said the fundamental counting principle tells us if we have a certain number of tasks and we want to know the number of ways we can complete all the tasks in sequence, we multiply the number of ways we can complete each individual task. We multiply all those numbers together. So this is that where if you had 5 different appetizers and 26 different drinks that you could choose from and 14 different entrees you can get and then 7 different desserts, you would do the 5 times the 26 times the 14 times the 7. That's the fundamental counting principle in 30 seconds. So now, what if you need to do multiple tasks, but each of those tasks requires a permutation or a combination in order to calculate the number of ways you could do it? This is actually a very popular question type. This is actually related to something in statistics called the hypergeometric distribution, which we're not going to go into uber detail about it, but I just wanted you to see it. The hypergeometric. Let's say there are 60 Democrats and 40 Republicans in the Senate. That's actually not true. Right now, the Republicans hold a Senate majority. There's more Republicans than Democrats, and who knows how that's going to shake up after the upcoming election here in a week or 9 days, I believe. But anyways, let's say there's 100 total people in the Senate. Now, let's say that we want to make a 5-person committee. And on that 5-person committee, well, since there's more Democrats than Republicans in the Senate, we want the committee to be roughly reflective of that. So we want 3 of the 5 committee members to be Democrats and 2 of them to be Republicans. How many different ways can we choose this committee of 5? Well, we have to first figure out the number of ways we could choose 3 Democrats out of 60 total. So number of ways to choose Democrats, more specifically, we want the number of ways we can choose 3 Democrats out of 60 total to be on the committee. That's going to be 60 because there's 60 Democrats, 60 C3. once they're on the committee, they're just a committee member. There's no distinct titles among committee members like president, vice president, treasurer, nothing like that. So that's why it's a combination. And so for Republicans, then it's clearly going to be of 40 Republicans, choose 2 of them. But we're not done. We got to compute each of these individual numbers, then multiply them together, because that's the number of ways we can both choose 3 Democrats out of 60 and 2 Republicans out of 40. So let me calculate those real quick. Using my deep magics, you are free to use your phone here. So 34,220 is going to be the number of ways we can choose 3 Democrats out of 60. And then 40C2 is going to be 780. 780, and we're going to multiply those 2 numbers together. I'm going to do 34,220 times 780. You're going to get a pretty large number out of it. That's okay. Your calculator can handle the heavy lifting. You're going to get a really large number. Let me double check that. Let me make sure I did not make a mistake, which is always a possibility. I did not make a mistake. 26,691,600. That's a lot. There's almost 27 million different committees you can make that will have 3 Democrats and 2 Republicans on it if you're picking from those pools. So a pretty interesting concept. Unfortunately, we're going to run out a little bit of time here, and I do want to get down to the last little part of chapter 5 here, which is connecting all of this with probability. And you're going to see that the connection is pretty cool. The connection is really cool, and it actually just kind of is logical and makes a little bit of sense. So let me pull up the last set of notes here for chapter 5. Dun dun. Real quick before I do that, I'm going to take attendance. Also, go ahead and realize that our exam is going to be this week, our 3rd exam. It covers chapters 5 and 6, but remember, chapter 6 is de-emphasized. So definitely I would read the textbook for chapter 6. I would watch some of the videos that are there in Canvas and work the homework for it, but I wouldn't strain over it. The questions are going to be pretty straightforward. You might have like 1 or 2 probability questions that are really just kind of a quick little punching of numbers into your calculator. That's how straightforward I think it's going to be. So let's take some quick attendance. Let's see who we have. Brooke Honeycutt. Very good. We've got Brooklyn Patton. I see you, and I shall gather you as attended. Let me pause the recording. So the last battle here over chapter 5. We're going to bring probability into the mix. We're going to talk about probability and how it's related to permutations and combinations. Remember, our very basic definition of probability, if you want to find the probability of an event, you count up the number of ways that your event could take place. We call that the number of successes, perhaps, the number of successful outcomes that are related to your event. And you divide just by the total number of possible outcomes. Remember earlier, we already kind of previewed this. There are 4 royal flushes possible in a deck of cards, and there are 2,598,960 possible 5-card hands in poker. So 4 divided by that really massive number is the probability that you're going to get a royal flush, and it's tiny. So Comedy Club has amateur night, which means that folks can come up there and try their hand at comedy. Good salt of the earth type folks. You don't have to be a professional. Six people want to go up there and do a little stand-up routine. Now, when I do a stand-up routine, I just rip off Jerry Seinfeld, and it's very bad. It's not funny. Nobody ever claps or laughs or anything. And so I gave up stand-up comedy, and now I just subject all of you to my comedy, and I hope you like it. And I know you don't, but I hope you do. So a comedy club has an amateur night. Six want to tell a joke. Ann, Bill, Carl, Dan, Emma, Fred. There's 4 men and 2 women there. Only 2 of them are going to get picked to tell their joke. What is the probability that the 2 people chosen are both women? The bottom number in our probability calculation is going to be the number of ways we can pick any 2 people from the group of 6. It's the total number of ways this experiment could turn out, with whether we get what we want or not. What we want is that both of them are women. What we want, at least for the purposes of calculating this combination, or this probability. And then it doesn't matter the order that you go up there and tell your joke. You still got chosen to tell your joke. So the bottom number is going to be the combination 6C2. We're bringing 6C back. So 6C2 is 15. There's 15 different groups of 2 that we can pull out of this group of 6 that can go up there and tell a joke. So I'm just going to erase this part and put it over here. So that's going to be the bottom number. That's going to be the total. That's going to be the denominator of our probability calculation. Now the top number, now we're just honing in on the 2 women. The top number, we want to, out of a group of 2 women, we want to pick 2 of them to be our people, to be our group of 2 that get to go tell a joke. So it is a combination of sorts, but it's a combination with the same N and R, which is fine, but that's going to be 1. And so the probability is 1 out of 15, which is, in probability terms, it's really the 6s repeating forever. It's 0.0666666666, and the 6s go on forever and ever. So we'll just round it to, I guess, 4 decimal places. It's fine. So if we just randomly pick the 2 people, there's only a 1 in 15 chance that both of them are going to be women. What is the probability that both are going to be men? Well, that's going to be different. The bottom number is going to be the same, though, because we're running the same experiment of just picking a group of 2 from a larger group of 6. So this is going to be 6C2, which is still 15. So our denominator is the exact same. So again, the denominator just counts up the number of ways this experiment could turn out, whether it's a turnout you want or not. The top number, though, now there are 4 total men. There are 4 total men, and you want to choose any 2 of them to be our joke tellers. So it's going to be 4C2, which is actually 6. So you're much more likely to get a group of 2 men up there telling jokes than you are to get a group of 2 women, simply because you had more men who were trying to go tell a joke. So that probability is going to be 6 over 15, which reduces to 2 over 5, or 0.4, and it's exactly 0.4. So there's a 40% chance. And then there's also the possibility that you're going to get 1 man and 1 woman who get to go up there and tell a joke, and that's going to be the third possibility. So there's 3 possibilities here. You can get 2 women, or you can get 1 man and 1 woman, which we did not calculate, or we can get 2 men up there being our joke tellers for the evening. Oh, here we go. What is the probability that, so we'll just calculate it here. What is the probability that it is a one man and 2 women who get to go up there and tell the jokes? That's the last one. The bottom number is the exact same. It is still going to be 6C2, because no matter what, you're just trying to find the number of ways you can make a group of 2 from a pool of 6 objects. The order doesn't matter. That's 15. The top number, though, Actually, we need to use the fundamental counting principle. Excuse me. The top number, we need to do two things. We need to pick one woman, not a woman, one woman out of two women that are possible that could make it in the group. We also need to pick one man out of four men, not 34, wow, who are in the group. And then each of these is technically a combination in and of itself. The number of ways you can pick one woman out of two is going to be 2C1. The number of ways you could pick one man out of four is going to be 4C1. And if you do each of those, 2C1 happens to be 2, 4C1 happens to be 4, and we multiply them together. And that's going to be 8. And that's going to make up the last piece of this. It's going to be 8. Well, I'll just say 8 for now. The probability is going to be 8 over 15. Eight over 15, which is going to be about, if we round, about that much. So the most likely outcome, if you're just picking a group at random, you're going to get one man and one woman. But it's possible you get two women. It's possible you get three men. There's two men. So cool stuff. We'll go a little bit longer than 9:05 like we normally do, just so I can get a couple more quick examples in. If you got to run, that's okay. But if you can go another 10 minutes, then we'll just stay in here and finish up a couple of these problems. I've already taken attendance, so if you got to go, that's fine. But otherwise, let's keep hanging out, y'all. Let's say a club consists of 5 men and 7 women. I'm going to assume this isn't like a nightclub, but that this is like a school club, you know, the Pokemon fan club. I tried to start a Pokemon fan club in college, and then I quickly realized that, well, I didn't want to do that. So there you go. 3 members are selected at random to attend a conference. Find the probability that the selected group will consist of 3 men. Well, in total, we have 12 total people. 5 plus 7. We have 12 total people in the club. So the denominator of our probability calculation from a group of 12 total, we need to select 3 of them. This is going to be the total number of ways, 12C3, that we can even run this experiment. And the 12C3 does not care about which group has this many men or this many women. It doesn't care. It counts all the possibilities. Some of the groups will have 0 men, some will have 1 man and 2 women, some will have 2 men and 1 woman, and so on. It doesn't care. It's impartial. The top number is going to be the number of ways of getting what we want. And when I say what we want, I don't mean what I personally care about. I don't care who makes it in this club. I just mean what we want in terms of calculating its probability. So the top number is going to be from a pool of 5 men. We want to choose 3 of them, any 3. It doesn't matter what 3 they are, they will count here. So we want to do 5C3 divided by 12C3. So 5C3 is going to be 10. 12C3, you need to go run a quick calculation. 12C3 is going to be 220. So in total, our probability is going to be 10 divided by 220, which is about not even 5%. Something like that, under 5% chance. Down here, what's the probability the group will consist of 3 women? Well, guess what? We're still going to use the same denominator because we're running the exact same experiment. So it's still going to be 12C3. On top, though, we want to pick a group of 3 out of 7 total women. So this is going to be 7C3. Now we just got to compute 7C3 there, Pilgrim, using our magics. And that's going to be 35. And now it's going to be 35. So now the women strike back here because there are more women in the club. So there's more possible ways of selecting your group to have 3 women in it than there are 3 men. 35 divided by 220 is going to be about 0.159. Now, if you're thinking, wait a minute, Josh, these 2 probabilities don't add up to 1. You're right. And that's because these aren't the only 2 possibilities. You could have all 3 of your group is men. You could have 2 of your group is men and 1 is a woman, which we have not calculated that probability. You could have 1 of your group is a man, 2 is women, something like that. So there's other possibilities than just these 2. And so that's why we haven't found all of them, is that's why they're not adding up to 100%. So we could calculate those. But I think there's a couple other things like that. So a lot of those are, whenever you're selecting and within your larger group, you have 2 kind of groups within them. You want to select a committee of 5 from 6 lawyers and 7 teachers. What's the probability they're all lawyers? Well, you need to do 6C5. That's going to be the number of ways of getting your group to have 5 lawyers in it, divided by, there's 7 plus 6, there's 13 total people that you could choose, make a group of 5 out of. So this calculation down here is going to be out of 6 lawyers, choose 5 of them, divided by out of 13 total people, period, choose 5 of them. Down here, what is the probability we get? Let's make it even more interesting. Well, let's just say 1 lawyer and 4 teachers. Well, out of 6 lawyers, choose 1 of them. Out of 7 teachers, choose 4 of them. And we need to multiply these 2 individual combinations. So do the individual combinations first. I'm going to put parentheses around them. And whatever you get for each of those numbers, divide, multiply them together, and then divide by, from a group of 13 total, choose 5 of them. Because 13C5 is the number of ways I can make my committee of 5 people, completely ignoring the divisions inside the group. Just 5 out of the 13, doesn't matter. So, and I'm doing this because I want to get a couple more in. In a lottery game, each player, in a lottery game, each player chooses 6 different numbers from 1 to 53. The order is not important. The order is not important. What is the probability of winning? Well, in the lottery, there's only one combination that wins. There's only one set of numbers you can pick. It doesn't matter what order you pick the numbers in. There's only one winning ticket. So your calculation here is going to have a 1 on top. There's only one winner. Out of, well, you choose 6 different numbers from a pool of 53. You don't care about the order, so this is going to be 53C6 down here. I'll do 53C6 as the probability. It's going to be a huge number. It's going to be really hilariously massive. And so the denominator on top, you're still just going to have one winning. The only winning combination maybe is like 12, 27, 34, 52, 19, 7, and 8 or something. That's the only winning numbers you can pick out of millions. There's hilarious. There's 22,957,480 different ways you could choose your 6 numbers, and only one of them is going to be the winner. So you have a tiny chance of winning that lottery, which is exactly how the lottery works. Do not make the lottery. Do not make it your don't make it your retirement plan. Oh, I'm just going to win the lottery around the time I feel like retiring. Don't do that. That's a terrible plan. Get an actual good retirement plan going where you save money over time. Maybe you get your company to match how much you're putting in your retirement account, which is a benefit most companies will offer when you work full time for them. Finally, suppose that a shipment of 120 electronic components contains 4 defective components. So let's do some quick numbers here. You've got 120 total components. 4, whether you know it or not, 4 are defective. That means 116 are working. 116 are not defective. They work just fine as they should. Now, here's what happens. The quality control engineer, which quality control for a company, think Creed from The Office, quality control is almost just a fancy word for statistician, because quality control is all statistics, practically. But to determine whether the shipment should be accepted, a quality control engineer randomly selects 4 of the components to test them. If 1 or more is defective, the shipment is rejected. What is the probability that the shipment is rejected? So the shipment is rejected if at least 1 of the 4 sampled components is defective. So out of 120, the quality control person's just going to go randomly pick 4 of them. There's no guarantee they're even going to get a defective in that group. It's totally possible they get all 4 they get from the working group, but it's possible they do get some defects. Now we want to know the probability that 1 or more is defective. We want the probability that 1 or more are defective, but we're going to use the complement rule and say we're just going to find the one minus the probability that none are defective. I'm going a little quick here because we're almost out of time. Now the probability that none are defective, we need to do some combinations here. We need to calculate the probability or the total number of ways I can select 4 total objects out of the 120. It's going to be 120 C4. That's the total number of ways I could select any 4 objects out of 120. I'll even put a little spacing in there. And then I want to get the number of ways I can select 4 of which that are non-defective. Well, there's 116 that are non-defective that are working. And so this is going to be the probability calculation we do. We do that one real quick. 116 C4. Probably going to be a pretty large number. Yes, it is. I'll just pop them down here. 120 C4. It's going to be on bottom here. And what you're going to end up with is going to be about 0.128. So there's a pretty high chance that even though there's only 4 defective components out of 120, there's about a 0.128% or 12.8% chance that at least one's going to be defective from the sample, and thus we're going to have to reject the whole shipment. So even though only a small part of them are defective, we may have to reject the shipment with a 12.8% chance. Okay, y'all have a great day. Your test, you can take it anytime Tuesday or Wednesday, but you can just take it Wednesday. Remember, we're not meeting on Wednesday because that's an exam day. Thank you guys. Have a great day.